The topic of this presentation is the effect of build thickness on fatigue behavior of Ti6-4 titanium alloy produced by electron beam melting. I am Razavi and I'm presenting this research for you. So these are the outlines of the presentation. Starting with introduction. The parts produced by additive manufacturing, they usually have specific design methods which results in complex geometries. These parts have been produced in a way to eliminate assembly of the parts and eliminate joining methods and produce the part, the component as one single part without the need of welding or other joining techniques. This would result in complex geometries with different morphologies of the geometries and also different thicknesses. And eventually, this variation in the geometry of the part would result in different strategies that the machine is using for printing the part, and eventually this can result in variation in the microstructure of the material and mechanical properties. The aim of this research, as the first step, is to study the build thickness effect on the mechanical properties. 3 sets of specimens for this aim were produced with EBM technique with maximum power of 3000 watt, hatch line offset of 200 micrometer, layer height of 90 micrometer, and with a powder size ranging between 40 to 105 micrometer. The build thicknesses were 5, 3, and 1 millimeter, and they were produced using titanium powder, titanium grade 5. This titanium alloy has two main phases of alpha and beta, which have structures of HCP and BCC. We performed microstructure analysis on the specimens that were produced. We took samples out of them, and here you can see the microstructure on the left hand side and microstructure on the right hand side. Looking at the microstructure, we can see that the prior beta grains are elongated along the length of the specimen, which is the same direction as the manufacturing of the specimen because they were produced vertically. So the heat transfer is vertical to the build stage, and if we look closer to these prior beta grains, we can see the microstructure of the material, which is shown by numbers from 1 to 5. Here you can see the boundary between two prior beta grains, and you can see on the boundary we have alpha phase, which is shown by number 1, and on one side, or let's say both sides of it, we have alpha lamella, which are alpha grains decorated in between using a beta phase. Number 3 shows the basket weave microstructure, which is also known as Widmanstätten, and also we had some larger alpha lats and also some random equiax alpha grain within the prior beta grain. So looking at the microstructure in different samples with different thicknesses, we could observe these microstructures that are shown here. The different rows show different build thicknesses from 1 to 5, and different columns show different microstructure from lamella basket weave to large alpha grains. We can see that the width of the alpha grain changes from 0.7 micrometer to 1.3 micrometer and 1.9 micrometer for the cases of 3 millimeter and 5 millimeter build thickness. This is a considerable change in the size of the microstructure, but what is the reason for this? The main reason is shown here schematically. If you look at the schematic view of the specimen with different thicknesses, we can see that the hatch lines have different numbers for different thicknesses. So the lower the thickness, the fewer number of hatch lines we have, and this would result in different thermal histories in the specimen, and eventually it would reduce smaller thermal gradient in the thinner parts and larger thermal gradient in the thicker parts. This larger thermal gradient in the thicker part would result and would help the grains to grow longer and larger, and that is what we observed from the microstructural analysis. So we want to see what is this effect on the mechanical properties of the material. As first step, we performed some microhardness analysis on the specimens with different thicknesses. We could observe that the highest microhardness is obtained for the thinnest specimen, and the highest value was 413 almost, and this value was reduced to 386 for the specimen that was thicker with a thickness of 5 millimeter. But overall, in all cases of EBM specimens, the microhardness was higher than the value reported or observed for wrought material with equiax alpha grains. After performing tensile test on the specimen, we could observe that the highest strength was observed for the specimens produced with 1 millimeter thickness, the thinnest specimen. So the finer the grain, the highest is the strength. But on the other side, the elongation at failure for this sample was 3.5%. That is almost a quarter of the value reported for 5 millimeter specimens. So this is a considerable change in the values or in the tensile properties of different specimens with different thicknesses. And this is mainly related to the microstructure that we obtained in the previous steps. So larger build thicknesses, larger grains, and eventually higher elongation at failure. We perform also fatigue test on the specimens. We expected the thinnest specimens to have higher fatigue strength because they have finer microstructure, but it was the opposite. So we can see that the thinner the specimen, the lower is the fatigue strength. The lowest fatigue strength was 129 megapascal for the thinnest specimen, and it was increased to 152 megapascal for the part that was 5 millimeter. Looking at the scatter index in the specimens, we can see that the scatter of the result is increasing by reducing the build thickness. So we had the highest scatter of 1.38 for the specimen that had 1 millimeter build thickness, while this value was equal to 1.2 for the specimen with 5 millimeter thickness. So the thinner the part, the higher is the scatter. Comparing these different cases, we could again see that the weakest one is the thinnest specimen, but overall all three cases are well within the range that have been reported previously in the literature for EBM specimens. Of course, with machining we can improve a bit the fatigue properties, which is shown here in red, but still it's far from the conventional material, and we may need to perform some additional post-treatments like heap to eliminate the internal porosity, and also together applying heap and machining would improve the fatigue life to a level almost the same as conventional material. Looking at overview of fatigue data, we can see that in all cases of EBM specimen, the fatigue strength was lower than SLM specimen that was stress relieved. And this change and this difference between the fatigue strength can be attributed to two things. First, the surface roughness of EBM specimens is usually 3 times higher than SLM specimens. So SLM parts usually have surface roughness of 10 micrometer in average, according to the literature. But EBM specimens have a surface roughness that is in average 30 micrometer. In both cases, since we have as-built surface, the fatigue strength values are lower than the one for conventional material. And one more thing that is important is that for SLM parts, the microstructures are quite fine, and there is the possibility to have martensitic phases in SLM parts that they don't exist in EBM parts. That can be also another reason that we are getting higher fatigue strength here. So overall, by reducing the build thickness, we have smaller grain size, larger surface to volume ratio, larger scatter index, and smaller inverse slope, or let's say higher slope of the Wöhler curves. Higher slope of the Wöhler curve in this plot shows higher effect of the geometrical discontinuities, or the surface roughness in this case, which can be attributed to the ratio between the size of the micro notches on the surface to the thickness of the specimen. Looking at the failure mechanisms in this material, we can see that it has different stages from stable fatigue crack growth to quasi-stable fatigue crack growth, which has the striation, and we have unstable fatigue crack growth, which is a mixture of striation and ductile dimple, and eventually we have ductile failure. In the case of stable fatigue crack growth, in an initiation phase, we can see some texture that is due to the microstructure of the material. If we compare different cases with different thicknesses, we can see that the size of a stable fatigue crack growth region is increasing by increasing the thickness, and that expectedly would increase the fatigue life. In addition to that, the initiation location is usually in multiple locations for the specimens with 1 millimeter thickness. That would help that would intensify the reduction of the fatigue life, and eventually we expect to have lower fatigue life for the thinner specimen, which is in accordance to what we observed from the tests. Looking closer at the initiation site, we can see that the texture at the initiation location is getting coarser by increasing the build thickness, which is again in agreement with what we observed in the microstructure analysis. So we know that for the thicker parts, we have larger microstructure, and this larger microstructure can be seen in the coarser texture of the initiation location. Some scatters were observed in 1 millimeter specimens that can be attributed to the presence of surface defects, and these surface defects can be explained as a result of lower number of scanning tracks on the specimen. Okay, looking at the conclusion of the part. The build thickness was found to have a strong effect on the material and surface condition, and consequently the fatigue properties of AM parts. The grain size we observed that is dependent on the build thickness. The higher the build thickness, the larger the grains. Due to higher surface roughness and presence of internal defect in EBM specimens, they resulted in the lower fatigue strength compared to SLM parts. The higher build thickness of EBM specimens provided higher ductility and lower hardness, which are again related to the microstructure that we observed in the specimen. The effect of surface roughness on high cycle fatigue behavior of specimen with smaller thickness was found to be greater. Multiple fatigue crack initiation sites from different faces of this specimen resulted in a non-uniform fracture surface. The microstructural evaluation of the fatigue crack initiation site revealed coarser texture on the fracture surface of thicker specimen as a result of larger grain size. Although finer grain size is favorable for higher high cycle fatigue resistance, however, the fatigue resistance of thin specimen with fine grains was lower than that of the thicker specimens. This was attributed to the higher surface to volume ratio and random deep surface defect in the thin specimen with 1 millimeter thickness. Thank you for your attention.